Welcome, everyone. This is part 5 in our series on methods and metrics. We're going to be talking about essential selected topics in model evaluation in our field. Here's our overview. I'd like to start by talking about baselines and their role in experimental comparisons. Then we'll discuss hyperparameter optimization, both the process and the motivations, as well as compromises that you might have to make due to resource constraints and other constraints. We'll touch briefly on classifier comparison, which is a topic we covered in the sentiment analysis unit. And then we'll close with 2 topics that are really pressing for deep learning models, which is assessing models without convergence and the role of random parameter initialization in shaping experimental results. So let's begin with baselines. The fundamental insight here is that in our field, evaluation numbers can never be understood properly in isolation. Let's consider 2 extreme cases. Suppose your system gets 0.95 F1, then you might feel like you can declare victory at that point. But it will be natural for people who are consuming your results to ask, well, is the task too easy? Is it really an achievement that you got 0.95, or would even simpler systems have achieved something similar? At the other end of the spectrum, suppose your system gets 0.6 F1. You might think that that means you haven't gotten traction, but we should ask 2 questions. First, what do humans get as a kind of upper bound? And also, what would a random classifier get? And if your 0.6 is really different from the random classifier and human performance is kind of low, we might then see that this 0.6 F1 is a real achievement. And that kind of shows you that baselines are just crucial for strong experiments in our field. So defining baselines for you should not be an afterthought, but rather central to how you define your overall hypothesis. Baselines are really important for building a persuasive case, and they can be used to illuminate specific aspects of the problem that you're tackling and specific virtues of your proposed system. What this really comes down to is right from the start, you might be saying, for example, here's a baseline model, here's my proposed modification of it. And the way we test your hypothesis is by comparing the performance of those 2 systems. In that context, you can see that the baseline is playing a crucial role in quantifying the extent to which your hypothesis is true. And therefore, careful model comparisons at that level are going to be really fundamental to successful pursuit of the hypothesis. When in doubt, you could include random baselines in your results table. They're very easy to set up and can illuminate what it's like if we're just making random predictions. And here I'm showing you that scikit-learn kind of has you covered on this point. They have 2 classes, dummy classifier and dummy regressor, each with a wide range of different ways that they can make random guesses based on the data. And I would encourage you to use these classes because it will make it easy for you to fit the random baselines into your overall experimental pipeline, which will reduce the amount of code that you have to write and possibly avoid bugs that might come from implementing these baselines yourself. So strongly encouraged. And kind of at the other end of the spectrum, you might think for your task whether there are task-specific baselines that you should be considering, because they might reveal something about the data set or the problem or the way people are going about modeling the problem. We saw an example of this before in the context of natural language inference. We saw that hypothesis-only baselines tended to make predictions that were as good as 0.65 to 0.70 F1, which is substantially better than the baseline random chance, which would be at about 0.33. And that's revealing to us that when we measure performance, we should really be thinking about gains above that hypothesis-only baseline. Comparisons against random chance are going to vastly overstate the extent to which we have made meaningful progress on those data sets. The story of the story close task is somewhat similar. Here, the task is to distinguish between a coherent and incoherent ending for a story. And people observed that systems that looked only at the ending options were able to do really well. There is some bias in coherent and incoherent continuations that leads them to be pretty good evidence for making this classification decision. Again, you might think that that reveals that there's a fundamental problem with the data set, and that might be true, but another perspective is simply that when we do comparisons and think about model performance, it should be with this as the baseline and not random guessing. Okay, let's talk about hyperparameter optimization. We discussed this in our unit on sentiment analysis, and we walked through some of the rationale. Let me quickly reiterate the full case for this. First, hyperparameter optimization might be crucial for obtaining the best version of your model that you can, which might be your fundamental goal. Probably for any modern model that you're looking at, there is a wide range of hyperparameters, and we might know that different settings of them lead to very different outcomes. So it's in your best interest to do hyperparameter search to put your model in the very best light. We also talked at length about how this is a crucial step in conducting fair comparisons between models. It's really important that when you conduct a comparison, you not put one model in its best light with its best hyperparameter settings and have all the other models be kind of randomly chosen or even poorly chosen hyperparameter settings, because that would lead to unfair comparisons and exaggerate differences between the models. What we want to do is compare the models all with their best possible hyperparameter settings, and that implies doing extensive search to find those settings. And the third motivation you might have is just to understand the stability of your architecture. We might want to know for some large space of hyperparameters which ones really matter for final performance, maybe which ones lead to really degenerate solutions, and which space of hyperparameters overall perform the best, so that we have more than just a single set of parameters that work well, but maybe real insights into the overall settings of the models that are really good. There's one more rule that I need to reiterate here. All hyperparameter tuning must be done only on train and development data. It is a sin in our field to do any kind of hyperparameter tuning on a test set. All that tuning should happen outside of the test set. And then as usual, you get one run on the test set with your chosen parameters. And that is the number that you report as performance on the test data. That's the only way that we can really get a look at how these systems behave on completely unseen data. So this is really crucial for understanding progress in our field. Now, hyperparameter optimization, as you can imagine, can get very expensive. And let's review that and then talk about some compromises. Right? The ideal for hyperparameter optimization is that you identify a large set of values for your model. You create a list of all the combinations of those values. This will be the cross product of all the values of the features that you identified. And then for each of the settings, you should cross-validate it on the available training data. And then choose the settings that did the best at step 3, train on all the training data using those settings, and then finally evaluate on the test data. That is the ideal here. And let's just think about how that's actually going to work. Suppose for our example that we have one hyperparameter and it has 5 values. And we have a second hyperparameter with 10 values. Then the cross product is going to lead us to have 50 total settings for those hyperparameters. Suppose we add a third hyperparameter with 2 values. Now the number of settings that we have has jumped up to 100. If we want to do 5-fold cross-validation to select those optimal parameters, then we are talking about doing 500 different experiments. And that's probably perfectly fine if you're dealing with a small linear model with some hand-built features. But if you are fitting a large transformer-based model where each experiment takes you up to 1 day, this is going to be prohibitively expensive in terms of time or compute resources. And that's going to compel us to make some compromises. This is the bottom line here. The above picture, that ideal, is untenable as a set of laws for our scientific community. If we adopted it, then complex models trained on large data sets would end up disfavored, and only the very wealthy would be able to participate. And just to give you a glimpse of just how expensive this could get, here's a quotation from this nice paper on NLP and machine learning for healthcare. In their supplementary materials, they report that performance on all of the above neural networks was tuned automatically using Google Vizier with a total of over 200,000 GPU hours. For me as a private citizen, that could easily cost $500,000 just for the process of hyperparameter optimization. And that's what I mean by this being kind of fundamentally untenable for us. So what should we do in response? We need a pragmatic response here. Here are some steps that you take to alleviate the problem in what I view as kind of descending order of attractiveness. So starting with the best option, you could do some random sampling and maybe guided sampling to explore a large space of hyperparameters on a fixed computational budget. You could do search based on just a few epochs of training, right? Rather than allowing your model to run for many epochs, which could take a whole day, you might select hyperparameters based on 1 or 2 epochs on the assumption that settings that are good at the start will remain good and settings that are bad at the start will remain bad. That's a heuristic assumption, but it seems reasonable. You could possibly bolster it with some learning curves and so forth. And that could vastly cut down on the amount that you have to spend in this search process. You could also search based on subsets of the data. This would be another kind of compromise. However, because a lot of hyperparameters are dependent on data set size, think of regularization terms, this might be riskier than the version in 2 there, where we just trained for a few epochs. You also might do some heuristic search, maybe by defining which hyperparameters matter less and then set those by hand based on this heuristic search. And then you might just describe that process in the paper that, via a few observations, you made some guesses about parameters that you could fix and therefore explored a smaller subset of the space that you might have liked to explore. Again, I think if you make the case and you're clear about this, readers will be receptive because we're aware of the costs. You could also find optimal hyperparameters via a single split of your data and use them for all subsequent splits. That would be justified if the splits are very similar and your model performance is very stable. And that would reduce all that cross-validation that did cause the number of experiments we had to run to jump up by a large amount. And finally, you might adopt others' choices. Now, the skeptic will complain that these findings don't translate to new data sets, but it could be the only option that you just observe, for example, that for some very large model, the original authors use settings X, Y, and Z, and you might simply adopt them, even knowing that your data set or your task might call for different optimal settings. It isn't the best, but if it's the only thing that you can afford, it's certainly a reasonable case to make. Finally, some tools for hyperparameter search. As usual, scikit-learn has a bunch of great tools for this: grid search, randomized search, and halving grid search. Grid search will be the most expensive, randomized search the least expensive, and halving grid search will help you kind of strategically navigate through the space of hyperparameters. And if you want to go even further in that direction, the scikit optimized package offers a bunch of tools for doing model-based, performance-driven exploration of a space of hyperparameters, and that could be very effective indeed. All right, let's talk briefly about classifier comparison. It's a topic we've reviewed before, but I'll just briefly recap. The scenario is this: suppose you've assessed 2 classifier models. Their performance is probably different to some degree numerically. What can be done to establish whether those models are different in some meaningful sense? As we've discussed, I think guidance from the literature is that first we could cover practical differences. If you just observe that one model makes 10,000 more highly important predictions than another, then that might be sufficient to make the case that it's the better model. For differences that are narrower, again, the guidance is that we might use confidence intervals on repeated runs or the Wilcoxon signed rank test to get a single summary statistic of whether or not the different runs are truly different in their means and variance. You could use McNemar's test if you can only afford to run one experiment, whereas the Wilcoxon and confidence intervals will require you to run 10 to 20 different experiments, which again could be prohibitively expensive. And in those situations, you might fall back to McNemar's test because it's less expensive and arguably better than nothing, especially in scenarios where it's hard to tell whether there are practical differences between the systems. Finally, let's talk about 2 topics that seem especially pressing in the context of large-scale deep learning models. And the first is assessing models without convergence, right? When working with linear models, convergence issues rarely arise because the models seem to converge quickly based on whatever threshold you've set, and convergence implies kind of maximized performance in a wide range of cases. With neural networks, however, convergence issues really take center stage. The models rarely converge, even based on liberal thresholds that you might set. They converge at different rates between runs, so it's hard to predict. And their performance on the test data is often heavily dependent on these differences, right? Sometimes a model with a low final error turns out to be great, and sometimes it turns out to be worse than one that finished with a higher error. Who really knows what's going on? Our only fallback in these situations is just do experiments and observe what seems to work the best. So I think a very natural and easy to implement response to this that proves highly effective is what I'm calling here incremental dev set testing. And this is just the idea that as training proceeds, we will regularly collect information about performance on some held out dev set as part of the training process. For example, at every 100th iteration, you could make predictions on that dev set and store those predictions for some kind of assessment. All the PyTorch models for our course have an early stopping parameter that will allow you to conduct experiments in this way and keep hold of what seem to be the best model performance-wise, and then report that based on the stopping criteria that you've set up. And with luck, heuristically, that will give you the best model in the fewest epochs. And the early stopping parameter has a bunch of different other settings that you can use to control exactly how it behaves, which might be important for particular model structures or data sets. Here's a bit of motivation for early stopping. You might be thinking, why not just let my model run to convergence if I possibly can? In the context of these large, very difficult optimization processes, that could lead you really far astray, right? So here is a picture of a deep learning model, and you can see its error going down very quickly over many iterations. And it looks like you might want to iterate out to even to 80 epochs of training. However, if you look at performance on that held up dev set, you see that this model actually very quickly reached its peak of performance. And then all that remaining training was just either wasting time or eroding the performance that you saw early on in the process. And this is exactly why, since this is our real goal here, you might want to do some kind of dev set testing with early stopping. And the final thing I'd want to say here is that all of this might lead us to get out of the mode of assuming that we should always be reporting one number to summarize our models. We're dealing with very powerful models. In the limit, they might be able to learn very complicated things, and we might want to ask different questions like how quickly can they learn and how effectively and how robustly. And that might imply that what we really want to do is not report summary tables of statistics, but rather full learning curves with confidence intervals. This is a picture from a paper that I was involved with, and I think it's illuminating to see a by-category breakdown of how the model is performing in addition to the overall average, because you can see that while this red model is arguably much better than the yellow and the gray overall, it's kind of hard to distinguish it globally from this blue model. But for various of the subcategories, you do see some differences, whereas for others, you do see that they're kind of indistinguishable. It's a very rich picture. You can also see that early on for some of these categories, some of these models are really differentiated. They learn more efficiently. Whereas by the time you've run out to 100,000 epochs, many of the model distinctions have disappeared. That's the kind of rich picture that is already giving us a sense for how different values and different goals we have might guide different choices about which model to use and different choices about how to optimize. And I would just love it if our field got into the habit of reporting this very full picture as opposed to reducing everything to a single number. The final topic is the role of random parameter initialization. This is kind of yet another hyperparameter that's in the background that's much more difficult to think about. Most deep learning models have their parameters initialized randomly, or many of those parameters are initialized randomly. This is clearly meaningful for these non-convex optimization problems that we're posing, but even simple models can also be impacted if you're dealing with very small data sets with very large feature spaces. In this classic paper here, these authors just observed that different initializations for neural sequence models that were doing named entity recognition led to statistically significantly different results. That is, one and the same model with a different random seed was performing in ways that looked significantly different on these data sets. And a number of recent systems actually turned out to be indistinguishable in terms of their raw performance once this source of variation was taken into account. And that's just a powerful example of how much a random seed could shape final performance in the context of models like this. Relatedly, at the other end of the spectrum, you can see catastrophic failure as a result of unlucky initialization. Some settings are great and some can be miserable failures. We don't really know ahead of time which will be which. And that means that we just have to be really attentive to how we're initializing these systems in a wide range of settings. And you'll notice that in the evaluation methods notebook that I've distributed as a companion to this lecture, I fit a simple feed-forward network, a very small one, on the classic XOR problem, which is one of the original motivating problems for using deep learning models at all. And what you see is that it succeeds about 8 out of 10 times, where the only thing that we're changing across these models is the way they are randomly initialized. And that again just shows you that this can be powerfully shaping final performance for our systems. And probably what we need to do is be thinking about this as yet another hyperparameter that we need to tune and optimize along with all the rest.